Welcome to session 3 of electronic structure theory. Now in this session, what we'll introduce is the idea that that whole Hartree-Fock approximation that said that an electron interacts with the other electrons in the molecule in some mean field or average way was really not true. It was an approximation that we introduced. The electrons, of course, are point particles that interact with one another by coulombically repelling one another. And so they actually undergo what we call a dynamical dance. That is, an electron doesn't move around in the molecule just thinking of the other electrons as being smeared out charge distributions. As one electron moves, the other electrons instantaneously adjust and undergo a dance where they move to different parts of the molecule while the first electron is moving somewhere. And of course, they all undergo this intricate many-body dance. And this many-body dance gives rise to things that we call cusps. That is, the wave function that describes where the electrons are have very sharp cusps as these two electrons come approaching one another, come in close contact with one another, because the electrons don't want to be there. So the probability that they are close to one another falls off very rapidly as they try to approach one another. So we have to introduce methods that go beyond this single determinate Hartree-Fock mean field picture, and we call these methods correlated methods. So in session 3, we'll primarily talk about what does correlation mean, what do cusps mean, and how do we try to introduce this dancing into the electronic wave function. So that's what we'll treat in session 3. So there's the third session on the electronic structure theory, and I want to begin by just taking us back to the end of last time, this idea that there's configuration state functions. And I want to just remind you of the two things that are wrong with this single determinate picture. One is when we try to break these chemical bonds homolytically, we have this problem where, for example, in the ethylene, the pi squared configuration just doesn't break apart right. It goes into half covalent and half ionic. So we have to do this thing where we, if you remember from 2 sessions ago, we take the pi squared and the pi star squared, and if you mix them together right with the right sign and everything, you can get something that is purely left-right and right-left, purely diradical. You get rid of the ionic character. So that's an example of where we have to mix together 2 configurations to get things to break apart correctly. We can't keep a single determinant. There's another case, and I've mentioned this last time too, where we have one configuration, say 1s squared, 2s squared, 2p squared carbon atom, but we don't want the triplet state, which could be represented by a single determinant. If we're interested in the singlet S state, there's just no single determinant that can be representing that thing. So you can never use Hartree-Fock there. It has nothing to do with breaking bonds. So Hartree-Fock, or any Slater determinant wave function, even without Hartree-Fock orbitals, they have this problem that you can't use them. Now, you say, well, what do we do? Well, we have to have more advanced techniques, configuration, interaction, and so forth. And that's where we're going in this kind of discussion. So just to remind you what the problems were. So what do we do when we have to improve beyond a single determinant? And we can improve because we have to, like with the singlet S, we need 3 determinants at least, or because we want to, that is, we just want a better wave function than the Hartree-Fock single determinant, which is predicated on that replacing the electron-electron repulsion by that mean field picture. And the most common thing we do in generality is called configuration interaction. Now, actually, this phrase gets used in a couple of different ways by myself and by many people in the community. Generally, when we take a wave function that we take to be a linear combination of unknown coefficients, we call them the CI coefficients, configuration, and then times various Slater determinants, we say we're doing CI. But when we talk technically about doing CI or MCSCF, what's called multi-component, sorry, that was a joke that hey, can you get rid of that joke, Jimmy? Okay. Multi-configurational self-consistent field theory. These are particular methodological devices that we use. But in general, anytime we take a linear combination of Slater determinants, we say we're doing configuration interaction. So why does this make sense to do this? Because, just to remind you, the spin orbitals that go into Hartree-Fock theory were obtained as eigenfunctions of a Hermitian operator, the Fock operator, Hartree-Fock Hamiltonian. They therefore form a complete set in principle. And Levdeen showed years ago that if you take products of these spin orbitals and anti-symmetrize them, that is, you form Slater determinants, that Slater determinants built out of orthonormal spin orbitals that themselves are a complete set, form a complete set of n-electron wave functions. So they're complete, and therefore you're allowed to expand any function as a linear combination of them times coefficients. So mathematically, we're allowed to do this. So what does it mean physically, though? And this is what I want to spend a fair amount of time now on when we talk about why do we do this kind of CI. And I remind you that sometimes we do it because we have to. There's more than 3 determinants just to get the right singlet and L equals 0, that is S state. Sometimes we do it because we want to homolytically cleave a bond. We have to mix the pi squared and the pi star squared determinant or configuration. But let's get a little bit better physical understanding of what it means when we combine 2 or more Slater determinants. And the most important identity that you want to have in mind is anytime we take one determinant and another determinant that differs from the first one by promotion of 2 electrons from some occupied orbital, say pi squared, to some previously unoccupied orbital, could be pi star squared, or it could be sigma star squared. And here in general I say, let's take phi alpha, phi beta, and excite them in the second determinant to phi prime alpha, phi prime beta. When we do that, okay, let me just pause for a moment. You could say, well, Jack, isn't the first term, if you have a Slater determinant, wouldn't you expect that your first most important thing to do to go beyond that would be single excitations, where you replace one spin orbital here by an excited spin orbital? I say, well, Brillouin theorem, remember Brillouin theorem showed us that those single excitations actually are not expected to be the most important first corrections to our wave function. Double excitations might be expected to actually be the most important first correction to our wave function. Moreover, as I showed you just a moment ago, sometimes when we have pi squared, pi star squared, we have other reasons to expect why we want to put in a wave function that's some determinant and something that's differing by 2 spin orbitals. That's already arisen as one of our cases that we want to talk about. So what I want to just lead you through now here in a few minutes is just a very important identity that you just want to have glued in the back of your mind, that anytime you see a wave function and then all of a sudden you see a second term in the wave function that differs from the first term by promotion, as we call it, or excitation of 2 electrons from some orbital, phi, into some orbital, phi prime. That combination, coefficient, CI coefficient C1 times this determinant minus C2 times that determinant, that combination of 2 determinants can instead be rewritten, or that is rethought of, revisualized, as C1 over 2 times a combination of 2 determinants. And I want you to sort of walk with me through this. The first determinant has the alpha electron is occupying a spin orbital that's neither phi nor phi prime, but it's phi minus x phi prime, where x is the ratio of the C2 to the C1 coefficient square root. And then the beta electron is in an orbital that's phi plus x phi prime. Now, but then there's minus another determinant. So you say, Jack, you're not getting around this problem. There's still 2 determinants. I know. There's 2 determinants here. There are going to be 2 down here. We're not going to be able to express things as single determinant. We're doing CI. There are many determinants. And here there's at least 2. But the basic idea is that the first determinant involves one electron that's in an orbital that's phi minus x phi prime, alpha. The beta electron's in another orbital, phi plus x phi prime, beta. And then we have minus, and the other determinant involves the beta electron being in phi minus x phi prime, while the alpha electron is in phi plus x phi prime. So the way I want you to sort of think about this is when Michael Morse teaches you about how to write a singlet wave function. Say you have one electron that is in orbital A and one electron that's in orbital B. He tells you, well, you take A, B times alpha beta minus beta alpha over square root of 2. See, here we have A, B, alpha beta minus beta alpha. So these 2 determinants are nothing but a singlet coupling, alpha beta minus beta alpha, of A, B, where A means phi minus x phi prime and B means phi plus x phi prime. Now let's get specific here, because it's important that you understand what this means physically rather than just this. But this identity here is one that you want to commit to memory as much as possible. So let's think about, for example, suppose you had ethylene, which I've drawn here. We got the pi orbital and the pi star orbital. And suppose this orbital that we're calling phi is the pi bonding orbital. And suppose phi prime is the pi star anti-bonding orbital. So this identity that says take C1 times pi squared minus C2 times pi star squared, and it can be rethought of as C1 over 2 times, now what would this orbital here be? Phi minus x phi prime. Well, phi is pi. Phi prime is pi star. So phi minus x phi prime would say take the pi orbital and subtract off a little bit. Why a little bit? Because x is the ratio of C2 to C1. And suppose C1 is like 0.8 and C2 might be 0.5. Well, so you take 0.5 over 0.8, take the square root of it, that's x. So what you would do is take the pi orbital minus that x amount of the pi star orbital. See this pi orbital, and now you're going to subtract from it a little bit of the pi star orbital. What that does is where the pi orbital and pi star orbitals have similar, that is the same phase, you'll get a reduction. Whereas when they have opposite phase, you'll get a buildup. So for example, phi minus phi prime, x times phi prime, where phi is pi and phi prime is pi star, you'll end up with this guy that is what's called right polarized. It'll have buildup on the right carbon atom. The other orbital, phi plus x phi prime, or pi plus x pi star, will have a buildup instead on the left. So these two orbitals, phi minus x phi prime, phi plus x phi prime, they are two different orbitals. One of them has more amplitude on the left, one has more amplitude on the right. So let's just stop and say this equation one more time. The physical picture I want you to get is that when you take C1 times pi squared minus C2 times pi star squared, that can be thought of instead as forming a singlet coupled, alpha beta minus beta alpha, pair of two orbitals that are different. One orbital has most of the electron density on the left, one has most of the electron density on the right. So this is the electrons avoiding one another. They're undergoing electron pair correlations. So this mathematically is why it is that two determinants differing by two spin orbitals can be thought of as allowing the electrons to be in different orbitals. One of them is more on the left, while the other one's more on the right. So let me just say it one more time. The first term has the alpha electron in phi minus x phi prime. That means it's more on the right. It has the beta electron more on the left. Then we have minus the other determinant that's beta alpha has the beta electron more on the right, while the alpha electrons more on the left. So these electrons are avoiding one another by allowing this wave function to have two terms in it. See, they're not having to both be in the same region of space at the same time. So they're minimizing their Coulombic repulsions. So that in this case, we have a pi orbital and a pi star orbital that we have combined to form these left and right polarized pairs. We call this left-right polarization, I think for obvious reasons. They're on opposite sides of the molecule. The electrons are dancing that way. They're undergoing this dynamical dance. Now, in this case, the orbitals that you form, these so-called polarized orbital pairs, are left-right polarized because the pi and pi star orbitals differ in their phases, their lobes on the left and on the right. Another example is when we deal with alkaline earth atoms. I think many of us know that things like magnesium in its ground state, 1s squared, 2s squared, 2p6, 3s squared. That 3s squared determinant is a pretty good description of what the state is for magnesium, but a higher quality beyond Hartree-Fock description involves including in your CI wave function not just the 3s squared determinant, but minus a coefficient times 3px squared, minus a coefficient times 3py squared, minus a coefficient times 3pz squared. And those coefficients are the C2s in this case, and the coefficient C1 is the coefficient in front of the 3s squared. Now in that case, what you have is you're forming polarized orbital pairs that would be a 3s orbital plus or minus a little bit x of a 3px or a 3py or a 3pz. So here in this picture I've shown an s orbital with, say, a pz orbital, and I'm forming a plus or minus combination of them, and they essentially give sp hybrid looking orbitals with the electron being on the bottom or on the top of the nucleus, below or above it. So in this case, we talk about angular correlation. So when we mix an s orbital with the p orbital to form this kind of thing, what we're saying is that the two electrons dance. One electron, the alpha, let's say, is below the nucleus, while the beta electron's above the nucleus. But in the singlet couple, we also have to have the other determinant with the beta electron down here while the alpha's up there. So anytime we have these electron pairs where we have a squared and b squared determinant being mixed together, what you want to think of in your head is take this orbital and that orbital and take the plus and minus combinations of them with a little bit of this mixed in, and then look at those two polarized orbitals, and you can tell how do the electrons avoid one another. Now, I want to give you just a little bit more contact with this too, and we're going to talk more about this, but let's go back to this ethylene example for just a moment with these two determinants. Here we have the two polarized orbital pairs, and what I'm saying to you is even when we have ethylene at its equilibrium bond length, I want to make sure that I make the connection between the ethylene at its equilibrium bond length and this thing about twisting ethylene to break the bond. Because this kind of thing actually has two roles in our theory. One thing is that even at the equilibrium bond length of ethylene, what I'm saying is that it helps to have a wave function that does not just have the C1 times pi squared in it. You want to mix in a little bit. Now, how much you mix in, we're going to have to learn how to do CI or perturbation theory calculations, but a little bit of a determinant that is pi star squared gets mixed in, because even at the equilibrium bond length of ethylene, these are the pi orbitals that are lined up like this, no twisting at all, it still helps to let the electrons do this dance where they're one electron's on the right while the other electron's on the left, and then the beta electron can be on the right while the alpha electron's on the right, on the left. So this kind of CI mixing with X, the ratio of C2 over C1, being small is still essential. It's an important thing in treating the electron interactions beyond Hartree-Fock theory. So we call that dynamical correlation. So when we have these two electrons here, if we just describe the wave function as just pi squared, we would say that's Hartree-Fock. No correlation. Because the definition of correlation is anything beyond Hartree-Fock. Hartree-Fock says the electrons are in orbitals. The orbitals are just sort of average regions of space where the electron resides. They don't dynamically talk to one another. They only interact in a mean field sense. So what we're saying here is that if we want to let the electrons dynamically avoid one another and go beyond Hartree-Fock, we use this kind of two-determinant wave function, because that gives the dynamical left-right, or in the case of the alkaline earth atoms, angular correlation of the s and p electrons being above and below the nucleus. Or if I mixed in an s and a px and a py, then it would be left and right. If I mixed in an s squared and a x squared, it would be in and out. So this angular correlation comes into play there. That's important even when the molecule is in its equilibrium geometry. But the other thing I want to make sure that we understand here is when we do now talk about this situation of let's take the ethylene and do the breaking of the pi bond by twisting it, you see this exact same kind of two-determinant wave function is useful in that context, because now when I do this breaking of the bond, I have a case where the polarized orbital pairs are not just a little bit polarized, but I actually end up with one of them becomes the pi plus pi star, where x is equal to 1 essentially, and that's the electron as being totally in this orbital, and the other orbital ends up being pi minus pi star, which is the electron being in this orbital. So the same thing that lets me do the dancing left and right allows, when I break the bond, for one electron to end up here while the other electron ends up here. So this kind of CI mixing is important for two reasons. And we quantum chemists say dynamical correlation, that means the dancing at the equilibrium bond length, but also essential correlation, meaning that you absolutely need it to break the bond into covalent and not a mixture of covalent and ionic. So the CI is actually important in two different kinds of ways, dynamical and non-dynamical correlation. Okay, and that's what I've repeated here. So we have our identity again, that it's a good idea to commit this to memory, and sometimes we absolutely need to put that into play, because this C2 ends up being essentially equal to C1 at some geometries. And here's the example of it where we took the pi squared and the pi star squared, and we actually had to mix them with equal amplitude to cancel out the ionic part of this and the ionic part of this and keep only the diradical part. But sometimes we also have to have more than one determinant for getting the proper spin symmetry, like in the singlet S. And CI, that is mixing in more than just the Hartree-Fock wave function, though, is always important if you want to treat dynamical correlation. That is, even when you're in a geometry where you say, I think the Hartree-Fock determinant is just fine as a starting point, I agree. But you want to go beyond the starting point, and by doing this kind of CI mixing, you can let the electrons dance. You can let them undergo dynamical correlation, avoiding one another, staying in different regions of space from one another. So that's the dynamical correlation idea. So just one more time, if you don't have a single determinant, like in the singlet S of the of carbon atom, don't even bother doing a Hartree-Fock calculation. You got to do something that's beyond what we've talked about so far. Then there are other times when, for example, breaking the pi bond of the ethylene, you've got to include the more than one determinant. And then even when you are convincing yourself that Hartree-Fock is a reasonable starting point, you want to go beyond it, and that's the so-called dynamical correlation. Now, I think it's natural to say, well, I'm an organic chemist. I deal with closed shell molecules all the time. Do I really have to worry about this dynamical correlation? I don't break bonds. I mean, this is a naive point of view because you probably do bond breakings and chemical reactions. But so how important, how big is this effect of dynamical correlation? And this picture, I think, illustrates it pretty clearly, even though it's on a very simple situation. Okay, so just to repeat, we know that our true wave function doesn't have this mean field potential. It has a real electron-electron repulsion that causes the non-separability in the Schrodinger equation. We also know the true electron wave function has cusps. That is, the wave function at the nucleus has those sharp cusps, and the electron wave function, as two electrons come close to one another, has these sharp electron-electron cusps that we talked about in the first lecture. But in the Hartree-Fock theory, what we've done is we replace these electron-electron repulsions by this so-called mean field theory, the mean field potential, to form our unperturbed Hamiltonian, and that's how we got our Hartree-Fock orbitals. But let's just take a little picture now and sort of indicate or get an idea of the order of magnitudes of how big is the difference between the Hartree-Fock Hamiltonian and the real Hamiltonian. So here what I have is just for a beryllium atom. I understand it's a trivial little thing, but just we have a beryllium atom. At the nucleus, there's the nucleus of charge plus 4. And what we've done here, basically, is to make a plot of the blue line that's here, that's sort of smooth and lower, that's sort of symmetrical around 0, is the following. I've taken the Hartree-Fock 1s orbital of the beryllium atom, okay, phi 1s. I've taken phi 1s squared of r prime, and I've taken e squared over r minus r prime, and I've integrated over r prime. So this essentially is giving the mean field Hartree-Fock potential that an electron at some position r prime away from the nucleus, 1 angstrom, 2 angstroms. So what you're talking about here is if you're an electron in the beryllium atom, and I just ask you, what is your mean field Hartree-Fock Coulomb interaction with just the 1s orbital? Now there's more than just the 1s, I admit, but this is just one term. The basic idea is if you're an electron very far away, the potential is 0, of course, because the 1s electron is down near the nucleus. But as you approach that nucleus, you start to feel the electron cloud of the 1s orbital. It's the 1s squared charge density. And essentially that Coulomb potential as a function of where you are. So you start out far out, you come in. The potential goes up, hits a maximum near the nucleus, and then falls off again as you go to the other side of the atom. Now look at the magnitude of that. The maximum there is 100 electron volts. Electron volts should be pretty scary because a chemical bond, is like 4 electron volts in strength. So the Coulomb potential there is very strong. That's not surprising. Electron coming in, feeling a very tightly bound 1s electron, and it's trying to interact with that. Now, the news is worse than that, though. That's the Hartree-Fock mean field potential. So one thing to notice about it is the J, the Coulomb integrals, in this case is J1s. Those are big numbers, 100 electron volts. The other graph on here is the following. What we've done here is we've taken the beryllium atom nucleus at the origin, we've placed an electron at the maximum of the 1s orbital's density. So we take the 1s orbital, we square it, we multiply it by r squared to get the volume element right, and we look for a peak. And that peak happens to occur at, I think it's 0.13 angstroms. So we place a nucleus here, we place an electron 0.13 angstroms out from the nucleus, and we say, okay, hold that still for a minute, and now pretend that you're an electron. See, the first thing we did is pretend you're an electron coming in, and you feel the nucleus, and you feel the 1s cloud, the J1s. Now we're saying, no, don't do that. Put the nucleus here, put an electron, a negative charge sitting at 0.13 angstroms, and hold it fixed, and then bring you, the second electron, in, and ask, what is the potential that you now feel? Now, of course, as you come in and you come right next to this electron sitting there, you're going to feel a huge, infinite repulsive wall there. So what we've done here in this second graph is to take the difference between this repulsive wall that you would feel, and then on the other side, the wall will go away. We've plotted what's called the fluctuation potential. That is the 1 over R12 repulsion that you would feel due to this electron that's sitting still at the maximum of the 1s orbital, minus this blue thing, which is trying to represent what is the potential. See, the idea is that repulsive potential is the true thing, E squared over R12. This blue thing is trying to represent it in a mean field sense. So we're trying to say, what's the difference between the true potential and the mean field potential? And that's what's plotted in these dark, I think they're black-colored squares that are there. Now, there's some good news and some bad news. The bad news is there's still a very big potential there. It's got to go to infinity, actually, at 0.13 angstroms, but it goes up to where I've plotted it here is 200 eV. So this fluctuation potential is still a big number. The good news is it's what's called shorter range. That is, this blue potential is representing the average electrostatic interaction of an electron smeared over a 1s orbital interacting with you as you come in. That's a Coulomb interaction. That falls off very slowly as distance, 1 over distance. This fluctuation potential is the true Coulomb potential minus this averaged out thing, so the difference actually falls off more rapidly than coulombically. So it doesn't, the good news is the fluctuation potential does not decay as 1 over distance. It's much shorter range than that. But this thing is still huge. It still has very strong amplitude. So in quantum chemistry, one of the biggest problems that we face is these electron-electron avoidances. The difference between the true avoidance, coulombic, minus our mean field approximation to it is not a small number. The perturbation, the fluctuation potential is a strong potential. That should tell us that, well, probably first order and second order corrections, including where we treat the fluctuation potential as a perturbation, may not be very good. We might have to go to third order, fourth order, 10th order, 20th order. Perturbation theory might be a problem, and sometimes it is a problem. So the bad news basically is that even the best we can do with Hartree-Fock theory, giving the best orbitals, the ones that minimize the total energy of that single determinant, that potential that comes out of that, the mean field potential, is still a pretty tough, rough, not very accurate description of the real potential. And the real potential is hard to treat because it's non-separable, so this is a very difficult problem we have. Okay, so what we're faced with is that the electron-electron interactions are large, and the errors made in describing them by Hartree-Fock theory they're still large errors. Also, in Hartree-Fock theory, we have these product of spin orbitals, and we know that that doesn't allow any kind of cusp behavior in the wave function, because the wave function cusps come from knowing that two electrons are coming close to one another. So it turns out that in Hartree-Fock theory and methodologies that are based upon Hartree-Fock theory plus perturbative corrections, they have a very difficult time treating these so-called cusps, that is the wave function dropping off rapidly as the two electrons approach one another. We can use these so-called dynamical correlation methods, configuration interaction that lets this electron be over here while that electron's over there. That does help the electrons keep out of one another's way, but it doesn't explicitly put into the wave function the ability for two electrons to avoid one another if they come really close together. So there are some high-end methods that we call explicitly correlated methods that build into a wave function, not this so-called configuration interaction type thing where we expand the wave function in terms of Slater determinants, but they use a different way of writing the wave function. And I just want to take a couple of minutes to sort of express what that's all about and to tell you why basically very few people follow this route in electronic structure theory. So we know that the electron cusp condition should be obeyed. That is, the derivative of the wave function with respect to the distance between the particles, the two electrons k and l, should have some characteristic value as RKL goes to 0. When we try to write wave functions as linear combinations of Slater determinants just by themselves with coefficients, we really can't build that cusp in. So some people have come up with a technique where they take a CI wave function, multiply it by 1 plus a half the summation over R over K and L of RKL. In other words, right into the wave function, they parameterize it with this extra piece added in, and it turns out that extra piece allows a wave function of this form to have the correct cusp behavior. These are called explicitly correlated wave functions because their functional form has R12, R13, R23 right in the wave function. And you say, oh, that's good. Problem's done. We're home free. Why don't we just do this in our Gaussian and our games programs and so forth? The problem is when you take a wave function of this form and plug it into psi star h psi to try to evaluate an expression for its expectation value of its energy, you end up with some integrals, for example, that look like the one that I've written here. These are 4 electron integrals that are 16-dimensional. You know, where does all this stuff here come from? Well, for example, here I have R13 and R23. They would come, for example, from, see, we have a psi on the left and a psi on the right. The psi on the left will have a term, for example, that has R13 in it. The psi on the right will have a term that has R24 in it. The Hamiltonian in the middle will have a term that's 1 over R23. So just one of the particular terms that you would get in that integration using the Slater-Condon rules would involve that kind of junk in the middle, R13, R24, 1 over R23. And then on the left you would have some phi L, phi K for the electrons 1 and 2. And so bottom line is, though, because of these R13s, R24s, and 1 over R23s, you have 1, 2, 3, 4 electrons, each of which has an x, y, and a z, or an r theta phi degree of freedom. So that would be 3 degrees of freedom times 4 electrons. There's also a spin. That's why I say it's 16-dimensional. If you want to get really picky, it's only 12-dimensional because there's 4 electrons times r theta phi for each one. But this is a 12-dimensional integral. And these are nightmares. I mean, basically, people can't write codes for these things to make these things doable on modern-day computers, except for very little tiny atoms and molecules. People actually do this kind of stuff. So the bottom line is the computational implementation of these 12 or 16-dimensional integrals that are there just is unfeasible, except for very, very small special cases where you have to get very high accuracy. So people don't use explicitly correlated wave functions except in very special cases. So back to the deal now. So, and this is basically the end of our discussion of this for right now. We'll move on to other subjects in just a few minutes. So the basic idea is the most common and practical ways to treat electron correlation are to take some determinant. If you're lucky, it might be a dominant determinant, triplet P carbon. If you're unlucky, singlet S carbon, it's one of 3 dominant determinants whose coefficients you will maybe determine by the spin and spatial symmetry of your wave function. And then to mix in other determinants that put in this dancing, the dynamical correlation and the bond breaking. But then the problem is, okay, when you have wave functions of this kind, one question is, should you keep your Hartree-Fock orbitals out here in the determinants? And if you do, how do you then determine these C coefficients here? That's configuration interaction. Or that's Møller-Plesset perturbation theory. Other people say, wait a minute, maybe what we should do is get rid of the Hartree-Fock orbitals here because now we're having a multi-determinant wave function. Hartree-Fock was all single determinant based. Could we make a better choice of orbitals and a better choice of these C coefficients to get even a better wave function? That's called multi-configurational self-consistent field theory. So a lot of the rest of the discussion of methodologies in electronic structure theory now, we're going to be talking about wave functions of this form, coefficients times determinants, but how they will differ is the procedures by which they determine the coefficients and whether they do or do not use Hartree-Fock orbitals that are in these determinants. Hartree-Fock orbitals, as you know, they have some advantages, Koopman's theorem, Brillouin theorem, and so forth, but there are various methodologies we now need to explore. So that's what I mean by let's look a little bit deeper about how we determine these orbitals and the coefficients. Okay.